In this section, I'm going to help you in a couple of different ways. The operation of the calculator with binomial probabilities is generally not difficult, but understanding how you get to the point where you're actually using the technology to get your answer, that's usually the tricky part for students. So, to give you an overview that's very quick in terms of how to use the technology, well, there's two functions in your calculator that you would use together. So we have PDF, which takes three inputs, n, p, and x. And we also have binom CDF, which also takes three inputs, n, p, and x. Now the last input is actually optional. You can not put that last one in if you want, and it would give you an entire distribution. Generally speaking, we don't want the entire distribution, we just want one probability, so we usually include that. Now, the difference between the two comes down to these three characters. So binom PDF stands for a probability distribution function, and CDF stands for a cumulative distribution function. And the cumulative function is just a running sum of the PDF probabilities. Okay, so let's take a look at this example problem and see how we can use these together. So a certain type of cellular phone has multiple color options, but 38% of consumers purchase the silver model. If a random sample of 8 owners of this kind is randomly selected, find the probability that exactly 2 own silver phones, at most 5 own silver phones, and no more than 5 own silver phones, and then at least 3 own silver phones. Okay, starting with the first one. So in order to answer these, often the keywords that you're looking for are things like exactly 2 owning silver phones, at most 5, no more than 5, or at least 3. How do we go about doing this? How do we go about determining this? Well, one way is to just straight up memorize. And you can absolutely do that. There's a way in your packet of notes that should exemplify how to just straight up memorize using just translating the words into the formulas in the calculator. But there's a much better way of doing things. So first off, let me show you what the distribution looks like. So here I have a binomial distribution with 8 trials because we have 8 people randomly selected. Probability of success is 0.38, and what we're looking at here is a histogram of the probability distribution created if we had taken the function in our calculator binom PDF and repeatedly plugged in different values of x from 0, which is the minimum that we could use, up to 8. So what that represents is none of the people out of our sample have a silver phone, all the way up to all 8 having a silver phone. Now, just to show you that these probabilities are correct, we can come up with them if we just simply use binom PDF in the calculator. And to do that, we would do second distributions, come down to where we find the binom PDF function, and there's 3 inputs, n, which is 8 in this case, p, which is 0.38 in this case, and we'll just pick, say, 4 for the last input, just to check. All right, so what this does is it plugs it into a formula for binomial probabilities and outputs the answer. So 0.2157, we'll round it to, and that's exactly what we have right here. So if we had done that for every single value of x going from 0 up to 8, this would be the output. And if we graph those values on a histogram, this is what that histogram would look like. So that's where all this is coming from. Binom CDF, to understand where it's coming from. If we take cumulative distributions of the binom PDF values, that's where we get binom CDF. So 0.0218 is the first binom CDF. If I add to that 0.1071. So if I take 0.0218 plus 0.1071, then I get 0.1289, which is the next binomial CDF value. If I add to that 0.2297, then I'll get the next one, going in that order. Now, the calculator has a function that will give you those values directly if you just enter individual values of n, p, and whatever you want for x. So let's put in 4 again here. So I come up with 0.8557. So it's gone through and calculated all the binomial PDF values from 0 to 4, added it together, and just outputted 0.8557 directly for me. So that's what binomial CDF is doing. So to use these functions together to answer questions, we have to understand that. We have to know what it's doing first before it's even useful to try and begin. So if I want to know the probability that exactly 2 people out of 8 own silver phones, well, for exactly 2 people out of 8, then I want the number of people to be exactly 2. If I want it to be exactly 2, then that's the only outcome that qualifies. All right, so I could shade, for instance, this one bar. So the height of this bar is the probability that I want. Binomial PDF will give me that probability directly. So in this particular case, if I want to know what this probability is, I just use binomial PDF. Anytime the language is exactly a certain number of outcomes, we use binomial PDF. So if I did second distribution, come down here to binomial PDF, 8 is the number of trials, 0.38 is the probability of success, and 2 is the number of successes we want to occur, so 0.2297. Okay, that's our probability. Now, find the probability that at most 5 own silver phones. For something like at most 5, you have to think about what that means linguistically. So, at most 5, first think about, is it less than 5 or is it bigger than 5? Right? So if something is at most 5, it's going to be less than 5. Okay? Then, once you decide that, you need to come up with, is the endpoint included or not? So is 5 included in this group? All right, well, if it's at most 5, then it could be less than 5, but it also could include 5, and that would be at most 5. So what I would want is this shaded region here to be added together. So going from 0 up to 5, but including the 5. So I want to add together these probabilities right here. I could come over to this chart and I could add those together, but binomial CDF has already done that for me. It's already added together all of the probabilities given by binomial PDF from 0 up to a specific number. So what I can do in this case is simply use binomial CDF. I've got to scroll down to get to it, with 8.38, and the last input would be 5. And I get 0.9615, which is exactly what we expected. All right, for no more than 5. Okay, let's see how that changes. Well, if it's... Actually, I think I'm going to change that to just more than 5, because no more than 5 would be the same thing as at most 5. So that way we have a different question. All right, so find the probability that more than 5 own silver phones. Okay, so we go back to our chart. You don't have to draw this chart out. You just have to kind of be thinking in your head how you want to come up with your answer. So if it's more than 5, it's going to be bigger than 5, Okay, so 6 or more. But then you have to ask yourself, is 5 included? But, well, if it's more than 5, that's not going to include 5 because you start counting after 5. So more than 5 is just going to be from 6 up to the maximum we could do, which is 8. So I need to add together these group of values right here. So what I can do is I can still use Binomial CDF, but the problem with Binomial CDF is that it's always starting to add up the Binomial PDF values from 0 up. So if I wanted to count 6, 7, and 8 for me, it's not going to do that as is. However, what I can do is use a complement, because what happens is I can say that the probability that x is less than or equal to 5 is going to be the same thing as 1 minus the probability that x is greater than 6. All right, and that might take a minute to settle with you, but here's what's happening. We have the different values of x that can happen. All right, and x is going to range from 0 up to whatever n is. Now, wherever x is less than or equal to 5, that's this group of values right here. The values where x is greater than 6 is this group of values right here. Notice that that encompasses all the different outcomes in this experiment, 0 through 8, so that this group is complementary to this group. So if I can find the probability of this one, which is Binomial CDF, n, p, and x, I can get this value by taking its complement. So if I take 1 minus Binomial CDF, 8.38, and 5. So the Binomial CDF function is still only going to count up these values I've listed in green, but when I do the complement of them, that will give me the range of numbers that I'm actually interested in. So let's see what we come up with. So 1 minus, and then I need to go into the distributions menu to get Binomial CDF, 8.38, and 5. So that gives me 0.3852. And that was the probability that came up right here. Okay, the very last one is probably the most difficult one because we have to do two things at once here. So we want the probability that at least 3 own silver phones. So make sure you understand this logically first, what's meant by at least. So at least, just ask yourself, is it less than 3 or greater than 3 to begin with? So if it's at least, it's going to be bigger than 3, okay? So because 3 is the least value it can be. So the question is, are we including the 3? Well, if it's at least 3, that does include. So we'll start with 3 and go to 8. So these represent the values that I want the total of. Now, how do I get the calculator to give me that total? Well, if it's an area on the right-hand side, so I've got like the shaded bars on the right-hand side, I need to do a complement with Binomial CDF. But then the question is, if I'm doing a complement, where do I stop the counting? So Binomial CDF, if I try and come up with the white bars here with Binomial CDF, I would use 0, 1, and 2. So I would put my value of x for Binomial CDF to be 2. All right, and that would give me the sum of the white bars. The complement of that value is going to be the sum of these blue bars. So that's what I need to focus on. I need to come up with, I'll just grab the calculator and do it directly here. I need to get 1 minus, because I'm doing an area to the right. All right, then I will do binom CDF, then 8.38, and then these white bars stop at 2, okay? And that's going to be confusing if you don't think about this, or at least sketch this out to see it, because it's tempting, because the question involves the value 3, to throw a 3 in there, but we're not using the 3 in this case. We're using 2. That gives me the 0.6415, exactly what has shown up right here. So that's how we use the calculator in this case. If you found this too challenging, I would highly recommend you give the stats calculator a chance here. I actually designed the stats calculator to make these types of problems easier, because I know what a challenge the calculator's input method makes for you.